designing, manufacturing, installing, and maintaining the high-speed electronic computer, the largest and most complex computers ever built.
Hello everybody, and welcome to another episode of Building Better Systems. My name is Shpat Marina.
And I'm Joey Dodds.
Joey and I work at GAWA, a computer science R&D lab focused on hard problems in computer science and software and hardware and systems.
So today we're going to be joined by Gregory Malecha. I've known Gregory for quite a while now. We were grad students at around the same time, and we worked in related fields doing cock proofs and doing our best to make them go fast, which is quite a challenge. Gregory is now at a startup that uses formal methods. They're called Bedrock Systems. He's the head of the formal methods team there. We're going to talk with Gregory today a bit about what Bedrock Systems is doing. And one of the things that Bedrock Systems is doing that's really cool is they're bringing together systems engineers, people building low-level systems, and they're taking those people and bringing them together with a formal methods team. And the output is something that's going to be more trustworthy than anything else on the market. So we're going to go into detail with Gregory around that, and it should be a really fun conversation. Thanks for joining us, Gregory.
Thanks for having me.
You've been working with Bedrock Systems for a while now, doing some pretty heavyweight formal methods. Can you tell us a little bit about that?
Sure. Bedrock Systems has been around for about a little over 3 years now. I joined at the beginning. Essentially, what we're building is a secure compute stack that you can kind of trust from the bottom up. So this involves components like a microkernel, hypervisor, and user space built on top of it. And basically, the idea is that these are critical components that we run everything on top of these components. And so bugs in these components are, cross-cutting. They affect basically everyone who might be running your system. And they're, obviously very complicated pieces of code. You have to deal with things like page tables and things like that. And so there's a lot of value in getting them right to some extent.
So what you're saying is it's not enough to take those layers that you mentioned in isolation. You have to reason about how they interact with each other to get meaningful guarantees and to be able to trust that low-level stack, basically.
Yeah, it does factor out as a stack. So at each level, we establish some property, but you need to make sure that the property is strong enough to establish the next property on top of it. A lot of times you might think of things like, I bottom out and I prove that there's no null pointer dereferences in my code, but someone building on top of your API, just knowing there's no null pointer dereferences in your code doesn't really help them in proving, for example, that there's no null pointer dereferences in their own code, or that they're providing a service to someone who wants it, like banking or something like that. I guess one way you could think about it is if a customer comes to you and they don't say, write a program that doesn't have any null pointer dereferences. They say, write a program that, learns how to identify cats in images, and kind of null pointer dereferences aren't part of the spec. They're kind of an implicit thing. And we want to kind of establish a property that, the customer or, the client might immediately know. That's exactly what I want, as opposed to saying, well, yeah, I don't want those, but what are you actually giving me?
And usually those are the benefits,
those are the benefits. Yeah.
It doesn't break unexpectedly. At least the system below your application, well, actually, I don't know what the benefits of no chance of null pointer dereferences are. What are they?
What are the benefits of them? Well, it doesn't break unexpectedly, but there's many other reasons. There's a whole CVE database of the reasons why your code might break unexpectedly. So if I go in and tell you, you won't be affected by the first 50 of them, you might come back and say, what about the next 50? And I'll say, probably not. So this is a way of kind of saying none of them. Nothing, not even the thing that no one's thought of yet, will be a problem to you. And that's really important because not everybody first shares their exploit and then exploits you.
And that's really cool because the work you all are doing is fairly detailed at the end of the day. It involves, I think, some pretty advanced work. But at the end of the day, it sounds like you get to make some pretty straightforward claims about what people using your software can expect out of that detailed work. Is that the case?
Yeah, that's the case. So I think what we're working on establishing is something we're calling the bare metal property. And it's a property about our hypervisor stack. And essentially what it says is that anything that could happen, if you have a stack like, Windows, Linux, whatnot, and you run it on bare metal, a bare metal ARM CPU, for example, and then you take that same piece of code, the same bytes, exactly the same bytes, and you put it to run on our stack, what we're saying is that there's nothing that can happen on our stack that couldn't have also happened on that piece of hardware. And that's kind of like a transferability property that says, we don't mess you up. If there's a bug in the system running on top of us, it's not our fault. It's your fault. We can try to help you fix your bugs or provide introspection mechanisms, things like that, to watch your code or monitor it. But ultimately, we didn't cause the problem.
It's not our fault. It's your fault. It's a
you
great.
Try to say this in the nicest possible way.
Great marketing slogan. No, but I mean, if it is true that you get to the point where people can be, absolutely sure that what they're building on top it's not going to surprise them. I mean, that's amazing. Actually, then maybe that's a spin on that marketing slogan.
Yeah.
So essentially, you're working on everything from bare metal to the operating system that people can build on. Is that right, or is it kind of a lower than that, lower than the OS?
It basically starts at the microkernel and then goes up. We're not dealing with some of the complexities of compilers, but we do deal with the complexities of hardware devices like, serial devices, DMA devices, page tables, things like that are, you don't get to program yourself. Some hardware designer built them, but yeah, you have to program against them. So we deal with all of those problems.
This sounds really useful because one of the things I think we hear increasingly often is there's a big concern where people write a program in their local environment and they run it in a development environment, basically a place where it's easy to run day to day, and everything seems fine, and then they drop it into the sort of deployment and everything changes. And it sounds like a bit of what you're promising is that that's not going to happen. If other programs are running alongside your program, for example, it's not going to mess with what your program's doing, and it should behave the same way it was behaving in the other. Is that a way to summarize this bare metal property that you mentioned?
To some extent, yes. I mean, there's a boundary to it, right? Like, suppose you run 2 guests on top of the Bedrock stack. That's like having 2 physically different computers and running your guests on top of those. But if there's interaction between them, different scheduling decisions and things like that could occur, but maybe don't occur, that are not likely to occur in one situation, but are more likely to occur in another. There's not much we can do about that. Like, in some sense, testing gives you especially in concurrent code, gives you a relatively weak approximation of what your code can do. And I mean, we may uncover bugs that we can point to. It's actually a bug in your code, and you can come back and say, well, that's okay, it never occurred in my platform. Like, well, bump to the next version of your AMD hardware or something like that, and then you'll see it there. It's kind of like, to some extent, it exposes some of the assumptions you're making that you aren't cognizant of. If that makes sense.
This is sort of off track a little bit, but I would imagine that what you're working on gets compared to things like SCL4 often. Would you be able to kind of explain the difference or the where it sits in relation to that for the people who are aware of that?
Sure. So I'll just start a little bit earlier, I guess. SEL4 is a project out of Data 61 in Australia. They've been building this. Well, they built a microkernel, SEL4, and they've verified it. It runs on a few different platforms. And it's a great piece of software. I'm not going to say anything bad about it. It really is a great piece of software. And what we have at the core of our system is comparable in many cases to in many respects to SEL4. It's a microkernel built on capabilities, so the same sort of underlying microkernel families are in there. The same sort of ideas are in most of those systems. SEL4 kind of stops the proof at the microkernel, and we are SEL4 doesn't establish a bare metal property. To establish a bare metal property, they would have to verify a VMM, virtual devices, and things like that, and that's not part of what they're doing. So we're kind of starting with a slightly different microkernel, Nova. It's open source as well, and building a stack on top of that, and verifying Nova and the stack on top, and showing that we can actually compose these layers and establish that final bare metal property is a crucial difference between the two projects.
Super cool.
So one of the natural questions now that we've talked about SEL4 is that group was really seen as one of the original groups of proof engineers, people that are doing day in and day out large scale proof efforts. Do you view the team that you work with as roughly that?
Absolutely. We are currently hiring proof engineers.
Awesome. And tell us a bit about that. You and I, of course, did proofs through grad school. My experience with proofs when we moved to an industrial setting is that it starts feeling a little different. Does your team? Well, how big is your team, and how do they work together?
Right now, my team is around 10. We are, a lot of us are in Europe, Germany, on the East Coast, but we also have people on the West Coast. But one thing that's kind of different about the way Bedrock Systems approaches formal methods than the way other companies do is that we really think that it's very important to get formal methods in very early. And so they're not my team, but the goal is to get systems engineers who came to Bedrock Systems without any FM background also applying these techniques when they're writing their code, and when they're thinking about their code, their designs and things like that. So really, I guess that's one difference is like, when you're in your PhD, you're kind of insulated from everybody doing real work, writing real systems. And you're just focused on all these people who have also committed their lives to typing in Coq, for example. And in this case, most of my days are actually, most of the time during my week and a lot of the time during the people who worked for me, their weeks, is spent interfacing with, real developers who are, know a lot about underlying hardware and are thinking about, how do I make a VMM? And not necessarily as much about is this the appropriate adjoint of this category to make this theorem work out or something like that. Like, it's kind of a more practical application. And we think that's actually really useful. One thing that's nice about it is you can't sweep complicated problems under the rug. It really forces you to tackle the real problem, as opposed to what I did in grad school in many cases was kind of sweep some of the most complicated stuff under the rug, because the heart of the problem is this smaller thing, and we need to take a more holistic approach to some of these problems.
And maybe the complicated problem is not necessarily the hardest or most interesting mathematical thing right there, right then. It's about deployability or just something, interacting with the real world. Is that a fair categorization of that?
Absolutely, yeah. Sometimes the hard problem is, you have to run on ARM hardware, and ARM has a weird page table semantics, for example. And it's at a Popple paper or something like that, you'd be like, that's not really that important. I'll just have this simple thing. But the real world is a little bit more complex, and we like that complexity sometimes, and we don't like it other times. So, yeah.
But at the end of the day, when you're talking to an engineer that needs to make a system run, there's no escape, basically. Either the system doesn't work or it does from that point of view, and so you have to deal with things. One of the things that I find when we get into those situations, though, is that maybe with my grad student hat on, I didn't give the type of problems that arise out of that kind of situation enough credit. They end up being pretty fun to work on in maybe a slightly different kind of way, but pushing yourself outside of that comfort zone and dealing with some of the messier details is its own kind of fun, I'd say, when you're doing assurance work.
It certainly means that you need, a lot of times we find, I did this in grad school, we find some clever encoding that makes our problem really easy. And then you take your problem one step farther, you add one more feature to your programming language, you realize your entire encoding just falls apart. And so sometimes this means that gorgeous paper that showed how everything falls out for free, and you're just like, wow, this is amazing. Then you apply it to a real system. It's actually there's this other instruction called syscall, and it just blows your mind. And then you're like, actually, I have to throw all of that away. I can take the ideas, but the code isn't as useful anymore because, that one little assumption that you made on page 1, basically said, this is going to be an interesting read, but it's not going to help you directly. I think is a really interesting sort of thing. It's unfortunately more common than you would expect. But at the same time, I'm not trying to disparage academics. The great thing about that is they get to handle the very complex problems, so they actually push us forward in being able to do what we're able to do now.
Well, I was going to say this. We always get to this point. It's a hard give and take, because those are not the incentives in grad school, and the incentives aren't necessarily bad. I mean, you're pushing the envelope in other ways. Not always. These are huge, broad, sweeping generalizations. But
absolutely.
Yeah.
I mean, to be concrete, Joey worked on VST. We build on a system called Iris. These are separation logic systems. Without these systems, without the ideas of VST, and without the implementation and stuff in Iris, we would not be able to do a lot of what we do. We have extended some of these systems, but we wouldn't have the basis. We wouldn't have someone to go to and ask these hard questions. And be oh yeah, in this simpler setting, such and such works. You can use those to draw inspiration to solve the same problem or similar problems in more complicated settings. I think that's crucial.
Yeah, well, and to take it further, we have our tooling, you have your tooling, and there's some experiments that are things that we'd like to do where if someone asked maybe you should plug this into your tooling today, you'd say, no, that's insane. You have to try it out on a small toy example first, because it's going to be so much legwork to get this up and running in the full-blown usable version of the tool. If it doesn't work, it will have been a massive waste of time. So take it simpler up front, and we'll see if it works, and then we can start thinking about moving it into the stuff that's being applied.
Absolutely. One particular instance where this arises, I think, is, and it's especially true in the kind of OS low-level context, is interoperability between programming languages. So when I was in grad school, we focused on a programming language, and the idea of someone writing in another programming language was kind of ridiculous. Why would you write in another programming language? But, this is an inherent thing. Nova is written in C++. It doesn't know anything. The master controller, the userland that runs on top of it can be written in anything. And so that requires you to kind of go down to a little bit lower level and kind of establish principles that allow you to compose systems maybe at that lower level. But that gives you flexibility that you may not prioritize in academic work, but is actually really useful in practice.
So you mentioned you're spending a lot of time day to day talking with engineers that are not necessarily formal methods experts. Mm-hmm. Are those conversations mostly information gathering from you, or are you giving things to them as well?
It's definitely a give and take, and it's really, they tell us a lot of stuff around problems. They tell us about the way that they think about problems. And we try to take that and digest it and then come back with like abstractions that we find or ways to explain their abstractions that make them more amenable to verification, especially. So, I mean, an example would be a locking discipline. We're building a VMM. We have a locking discipline around the way that our CPUs can use memory. And, finding a way, our engineer said, like, here's how I think about things. We've got this locking system. And we kind of showed that you can express that locking discipline in this way in our system or in the separation logic system. And, he finds insights from that because it's, rather than having to explain to us for a half an hour, he says, oh, like these 5 definitions kind of characterize what's going on. And they abstract away the boring parts, the part that says you have to call this function and then that function. And they let you focus on, oh, like this is what's possible and this is what's not. And then he says, oh, maybe I'll need to add this feature in the future. How would that impact things? So it's really like a summary of what you're doing, but at a slightly more or deeper level than just seeing C method declarations or C function declarations, right? You get a little bit more about, what does this function is thread safe actually mean, as opposed to just you can use it thread safe. Yeah.
Mm-hmm. These are the engineers that are working on the software, not necessarily doing the verification. Is that right? So
engineers at Bedrock, non-formal methods engineers at Bedrock work predominantly on C++ code and writing specifications. So they write specifications, and we are working on, bringing people up to speed, having them be able to actually write their own proofs. And I mean, we expect that they will be able to write proofs about simple code initially, and then, ultimately get up to more complicated code. There will inevitably be places that are active research areas like, weak memory, things like that, are probably beyond what they'll be able to do in the long term. But I mean, the idea of the formal methods team is to really provide tools to support the sort of work they're doing, patterns. If your thing fits into this pattern, apply this technique, and hopefully we can build automation that, makes it easy to do that. And then obviously we also work on proofs that are just more difficult, like the really core concurrency abstractions and stuff like that require a lot of deep knowledge about what's going on and, require, that extra depth, I guess.
Sure. So just hold on. So it sounds like you have engineers that have nothing to do with formal methods, and they are writing specifications, which you can, as they write the code, they're writing specifications that then you can leverage to verify that.
Yes, that's true.
That's, in my experience, relatively rare. I wonder if you if you have anything to share about that process.
It's not easy. There's definitely a learning curve. Like, people go to grad school, people study this stuff for a long time, and taking someone who's very used to writing C code, low-level C code to tickle devices in just the right way, have obviously developed like different skill sets. But a lot of the things that we do in formal methods, the code that we like in formal methods is, I would say, well abstracted code, and most software engineers also like well abstracted, like well written code. If you give me some spaghetti code and I'm like, how am I supposed to understand this? And then you give me some nice, class hierarchy or whatnot, pick something appropriate for your topic. Don't just put objects on everything. But I mean, they like that too. And one thing that we can do actually, and is very attractive, is that if someone says, I've written this piece of code and we come back, here are some changes to it, it's often the case that that they like the new code better. That they say, I didn't see the abstraction that you saw, and we can show them like the specification that we would have had to write for your code would have been, twice as long, would have had kind of these odd caveats around these things, which are often the places where bugs arise. And you see like, oh, in this new implementation or this even slight reworking of the code, it now becomes more obvious. Things can become a little bit more dynamic. There's less coupling, and generally, I think people like that code and find it easier, more natural to program against. So I think that FM improves code, and I think, and I should say this up front, even if you never get to a QED, even if you never verify your code, if you apply formal methods techniques, or you listen to a podcast like this, or you read some documentation, like, I can think about formal methods, you will, I think, and from my experience, you will end up with better code, even if you never take the time to actually QED the proof at the end of the day.
Just thinking about it, in a way, affects what you do.
I think when formal methods goes well, it feels like, to an engineer, it feels like writing down stuff that you already know, basically. Like, engineers already spend their day trying to produce correct code, right? That's sort of undebatable. Nobody's out there like, you know what, I'm gonna mess this function up. This one I don't care about. Like, let's just dereference just everything and not worry about it. Null or not null. Everybody's trying to write correct code, and everybody's explaining internally to themselves, or hopefully to their teams through code reviews, why they have written correct code. And so, if we can sort of get starry-eyed and gaze off into the future of formal methods, eventually hopefully formal methods can get to the place where you're just writing down the stuff that you already know, and it feels so natural that at the end of the day, like, the computer's doing code review with you, basically. It's saying, hey, what, you said your code's right for this reason, but that doesn't quite match up. Let's revise this. And I think that is going to have to come from the tooling side, not from, like, we can't just say, like, hey, engineers, what's your problem? Why aren't you writing specs? We have to make the specs the kind of thing that engineers want to write. Because I think the will is there on that side if we can meet them, basically. And it sounds like you're taking steps in this direction, certainly.
Yeah, I think if you look at systems like Rust, Rust already, like, the delta between Rust and C is, in C you kind of get to do whatever you want, and in Rust, the type system will smack you on the head every time you do something wrong. And it's kind of like opting into specifications. It's opting into particular style. Here the type system is enforcing an invariant on your code, essentially. And it doesn't, at the end of the day, tell you that you are a VMM and that you are establishing the bare metal property, but it does give you the absence of null pointer dereferences and stuff like that. And so, that's one way. Like, I actually think of, like, Rust as kind of like formal methods light. You can get a strong safety guarantee. You also get this from other systems like OCaml and any type-safe language like this. But Rust showed that you could do it nicely in low-level code, and I think that we'll take ideas from go to the extreme and be able to do anything you want, and come from the other side, and they will meet in the middle. There will be a sweet spot, and there will always be places where you have to go farther, because thankfully not everyone is verifying page table code, but someone has to do it, and that's probably not going to fit in the Rust type system in a nice way. Though maybe someone will reply to your podcast and say, "I did that last week."
It sounds like you're really taking things step by step with the engineers you work with, starting off writing specs that feel comfortable, and maybe now you're starting to also see more interest in writing the proofs now that the value has been seen from the specs. Is that kind of the case?
Yeah. We actually went back and forth on this. I think it's an interesting thing. You can tell people to write specs, and you can show them how to write specs, and you can explain to them very well what a spec means. But, to some extent, until you can check your own spec, you'll be dissatisfied. I joined computer science. I became a computer scientist in part because if I wanted to test see if I got the right answer, I just ran it. And then if it came back and said yes, then I was like, okay, I got the right answer. And otherwise I was like, oh no, I got the wrong answer. I'll try it again. And engineers, we spent a lot of time teaching them, here's how you write a spec, here's what separation logic means, etc. And they kind of understand it at an academic level, maybe, until they can like go through and trace their code and say, oh, this spec's not going to work because this doesn't work or this doesn't work. That's when it becomes more real for them. And actually, that's where you get the real value. Because then you'll be like, oh, this thing that I wrote, like my spec is beautiful, but this place where I tried to implement it is really awkward. And that's where you'll often say, oh, my code is doing something that's maybe it shouldn't be doing. Maybe it's going to be hard to justify that's correct. And maybe there's a better way. Sometimes there's not a better way, and sometimes there's a slower, easier way. But a lot of times there's a equally fast, sometimes faster way that is actually easier to verify than what you wrote.
So I know this isn't what you all are doing, but I think it's a good question for formal methods. Is like, I think you identified something that I agree with, which is that writing specs alone isn't going to provide enough value for engineers to want to do it. You need to see that value expressed on the code, basically. Like, it needs to find mistakes that you wouldn't have otherwise caught, or help you organize things better. I'm curious for that particular problem. I know you all are going for full formal verification. I'm curious for the field of formal methods if we can see benefit out of things like testing from specs, if that might get to the same place. When we talk about teams adopting formal methods, not your goals are related to formal verification, but if we focus on the separate goal of how do we get people to adopt spec writing, I wonder if testing is enough.
It's an interesting question. I will say that some things are pretty hard to express via testing, especially concurrency. I mean, I go back and I think about the sort of verification that we do, the sort of code we write. Like, when I remove concurrency from the equation, like, why don't we just test everything? Like, this is so simple. We just run a bunch of tests. I mean, there's a lot of numbers, and you can run them all. You probably, and there's a lot of work that does this. Static analysis and things like that are ways to, get formal methods for kind of cheaper, at least. And they're great tools. Concurrency is another story, and there's not as many tools that are equipped to handle the complexities of concurrent applications. And so, I think that there's definitely a big cliff or a big mountain you have to cross, but I think actually that it's a teaching problem. And then once you can cross that, you will find that you will not understand how you survived without it. This is like and maybe this is just, I already drank the Kool-Aid. I already climbed up part of the mountain. Like, I don't want to go back. So, but I think like what I've seen is people who actually really understand the theory behind the formal methods. And increasingly, the people that we work with who don't have PhDs in computer science and formal methods understand that, like, there's real problems that I can talk about here that I was really hard to talk about previously. And I think that's, maybe we should just teach more formal methods. I guess that would help me in my hiring, but yeah, I think it would also improve the state of software overall.
I actually think that's, just to take a moment, that's one of the better pleas for people to maybe start learning about formal methods that I've heard, because it's like you don't know what you don't know, and you don't know how useful that might be, and you might be trying to do something very hard that might have a very simple solution that then you will never be able to do without later. And also it's a matter of, like, it almost sounds like vocabulary or a new language, or let's say music, right? There's amazing musicians that never need to learn a day of music theory to be amazing. And music theory can be very useful in you communicating what you're trying to say and talking to other musicians and actually maybe even bringing some of your ideas to existence. Maybe it's a contrived comparison, but it's interesting nevertheless.
I mean, on this topic, I was chatting with someone a while ago. He was a C programmer, C programmer, became a C++ programmer. Like, basically told me, like, I didn't understand how to program C++ until I went to Haskell. He said, OCaml wasn't pure enough for me. I had to go all the way to Haskell to really understand what I was doing or how to use C++ effectively. And I think, we do C++, and I wasn't a C++ programmer by day when I started at Bedrock Systems. So I do watch C++ Con and stuff like that, CPCon, and the talks there by many people are taking ideas from functional programming or other things. And a lot of the things that I see that they're saying, oh, the cool kids are doing this. It's like, yeah, that's more easily explained by formal methods than what you were doing before. So maybe if you follow the cool kids, at least to some extent, don't always follow the cool kids, but sometimes they're right.
So yeah, I'm curious about, I think you answered this question part way, but there are some things that you're doing at Bedrock Systems that, well, most of them sounds like they require the most correctness, the best of the top shelf of verification. I'm curious what your thoughts are on engineers who work on kind of regular systems and software that perhaps doesn't require that kind of absolute top best correctness, that are not in the world of formal methods. What are some good incremental ways to start building safer, more reliable systems and software that don't necessarily require them to be formal methods experts? Some of them sounds like part of that answer is look at some of these other languages that might inform how you do things. What else would you kind of bring to that table?
Well, I think learning more about formal methods is, I think, generally useful. And you can see this in a variety of ways. Like, if you are a C programmer or something like that, pick up a programming language like OCaml or Haskell. Haskell might be too scary, but I think OCaml is relatively tractable. There's good resources for it. I mean, we had this experience actually with our VMM engineer. He came to us knowing OCaml, and he picked up the ideas of formal methods relatively quickly. He had no formal methods training per se, but just being exposed to functional programming as an idea was really, really useful in overcoming that gap. If you're, more in like the Rust camp, if you're doing Rust, then you are kind of doing separation logic to some extent. And people say like, oh, I don't want to learn a proof assistant, not a new proof assistant. I don't want to learn a proof assistant. I don't want to do all these complicated things. But there are partial solutions to this. Like, if you say, I'm willing to remove side effects and switch to a functional language, you might think of things in a different way. And that might inform the way that you write code in JavaScript or C or something like that. And sometimes that makes for better code. And at least it gives you different ideas. You might think of, there's another way to think about this abstraction. How might that influence, my users or things like that in the future? I'm not sure if that's a total answer to your question.
I think it is. I mean, explore these other areas and bring some of that stuff into your own work. And this resonates with me. I don't do a lot of programming, really not at all, comparatively speaking, but just by osmosis, by being a Gawa for a while, whenever I get to do something that's extremely utilitarian, I'm trying to make something work just by, this idea of, think more functional and remove side effects as much as possible. I mean, it has made a huge difference like on some little things whenever I do it, and it feels good. So it makes sense.
Yeah, I think when we see really experienced programmers and good programmers are almost synonymous in some sense. I think like if you say someone's experienced, that's almost almost always a good thing in terms of what they're going to do. And so and we see this in programming, right? Sometimes we start writing a program and it has a pattern that like feels bad to us, right? And it's hard to explain why, but like you sort of get the sense that you've done this enough and you know that's not going to go well. And a lot of times that turns out to be right, basically. And what I'm hearing was functional programming, right? If you spend a long time in functional programming and all of a sudden you're writing like a super side effect heavy C++ program, and it's going to be really hard to track the effects that it has through the system, you're going to start developing some of those same feelings and instincts. And it sounds like it sounds like your impression also is that the C++ development strategy sort of as a community is broadly moving in this direction, which I think sounds like really good news. People are, as a community, some of these things that feel bad are sort of being treated as best practices and probably helping even people that aren't able to take the time, for example, to learn OCaml and to gain these insights on their own, to build patterns that help them be better from day to day. So that sounds like a really encouraging message.
Yeah, absolutely.
Gregory, you mentioned that you're hiring. I wonder if you wanna share a little bit about what you're looking for, just in case the perfect match is out there listening to this podcast right now.
Sure. We are hiring in a lot of areas. We're hiring on both my team, the formal methods group, as well as the more systemsy group. And obviously, we're looking for very different backgrounds. But interdisciplinary knowledge here is super useful. Like, if you are the sort of person who, you're a C hacker by day and an OCaml hacker by night, then you're an ideal candidate for us, because you probably have a great deal of knowledge about, how to tickle bits or how to set up, complicated systems that work together. And you also understand kind of the other side of things. And I think, the same thing can be said if you're a functional programmer by day and a C hacker by night, then if you join my team, then you won't have to learn about move semantics and things like that as much. But we're hiring in both areas and in many areas. So a lot of my team has PhDs, but it's not necessary. People with knowledge about Coq, separation logic, especially concurrent separation logic, as well as proof automation. That could be resolution theorem provers, it could be SMT, many sorts of things. And as well as on the other side, obviously we're building a system stack. So people with knowledge about devices, hardware platforms, things like that are all very important to the engineering efforts that we do.
You mentioned, at least on your team, you're looking for proof engineers.
Yep.
What does that look like day to day? Is it what would you highlight from working on your team that you'd like to share?
What does a proof engineer on my team do?
Yeah. You should be the interviewer.
Yeah. So what do proof engineers on my team do? They do a lot of things. They talk with non-proof engineers to figure out what code is supposed to do. They, might go to meetings and, learn about what the next feature is, and then they might interject their comments on how we should or should not do this. So we're involved in the design process, obviously. That's crucial for building effectively verified software. But we're also obviously on the back end of this thing. Like, okay, the code's been done, it's been specified. Let's actually prove it. And sometimes you have new insights from the proof that you kind of hand waved away this detail, and you say, actually, that didn't work. So there's components of that. There's also components of teaching, collaborating with people, learning what they think about when they're designing the system, and then, teaching what you think about when you hear about this or when you would design the system. And the idea is ultimately, to get better code across the board, more verifiable code, easier code to work with, more extensible code, et cetera. I should mention that last bit. We've found that well-architected code may take a little bit longer to write up front, but you don't spend the cost rewriting it when your feature set changes, right? And this is one thing that you can build a hyper customized library and you say, oh, it's perfect, it's verifiable. But then at the end of the day, you say, well, the one feature that it didn't support is what we needed. And now all of those carefully crafted assumptions kind of fall by the wayside and you're back to square one. And understanding those is really helpful in building software that lasts from release cycle to release cycle, as opposed to lasting only one or two release cycles.
Sounds like fun. It doesn't sound like you'll have much trouble keeping people engaged and providing lots of variety and excitement. So
no,
that sounds like a pretty good opportunity for somebody that fits.
I think it's a lot of fun. No one on my team has ever told me they've been bored. There's lots to do, and there's a lot of interesting problems. And some of it is typing, and that's inherent to everything, and some of it's really deep thinking, and a lot of it, I think, in the formal method side of things, is a nice combination of these two.
This was a great conversation. Thank you for joining us today, Gregory.
Thanks for having me.
It's a pleasure. This was another episode of Building Better Systems with Joey and I. We'll see you next time.